Alright, so we're going to be finding asymptotes in this section, starting off with perhaps one of the easier asymptotes to find, that's vertical asymptotes. It says if you have a rational function in the form of p of x over q of x, if you have it written in reduced form so that p and q have no common factors, then the vertical line x equals c will be a vertical asymptote for the function if and only if c is a real zero of the polynomial q. That's the denominator polynomial. So we're going to be looking for zeros in the denominator of the function. It's similar to what we would have done when we were looking for domain. In the past, we tried to find holes in the domain, places where the denominator was zero, perhaps, in a fraction. If you remember that from the past, there were several conditions for where a domain didn't exist. One of them was if you have division by zero, this would be places where f of x is undefined. And so we're using that same kind of concept here. We're going to be looking for when is this denominator equal to zero. If we can find those zeros of that polynomial, then that's where the vertical asymptotes are going to be. Like it says, as long as p and q have no common factors, though. So when we look at this first problem here, the numerator and denominator, they do have common factors. So we can't just set the denominator equal to zero. Okay, this would be close to what we need, but not exactly. Because if you did that, what you would find is that x minus 1 equals 0 or x plus 2 equals 0, and then you'd try to solve them both, and you see that 1 and negative 2 are both zeros of the denominator. But we can see from the graph that only one of them is an actual vertical asymptote. What really is occurring here in the original polynomial is that it has a hole at negative 2. That's not shown on the graph here right now because it was just a computer-generated graph. But if we wanted to be completely clear, there's actually a hole in the function if we're talking about the original function. Okay, so x cannot be 1, and also x cannot be negative 2 for the original polynomial. But what we have to do is actually reduce to a simpler form to find the location of the asymptotes. So as you can see, they share a common factor of x plus 2. So if we rewrite the thing as just 1 over x minus 1, then we've found the true location of the asymptote. You just set the x minus 1 part equal to 0 and solve for the vertical asymptote. Okay, so this here, let's see why he doesn't have a vertical asymptote. So let's see if we could factor that numerator. This guy will break up into x plus 2, x plus 1. It looks like the x plus 1s would cancel, leaving us with just x plus 2. And so, because he has no denominator, there's going to be no zeros of that denominator. Because of that, there's no vertical asymptote. Let's see what's next. This talks about horizontal and oblique asymptotes. So let's read the definition. So f of x equals p of x over q of x is a rational function. Let it be a rational function where p is an nth degree polynomial with leading coefficient an, and q is an mth degree polynomial with leading coefficient bm. It says if the degree of the numerator is less than the degree of the denominator, then the horizontal line y equals 0, which is the x-axis, is going to be a horizontal asymptote for the function. Let's just go to Desmos and see if we can play around with some different possibilities and we can see why this may be the case. So let's do f of x. We're looking for something where the degree of the numerator is less than the degree of the denominator. So I'll come up with a rational function that meets those criteria. We could have something like x over x squared, where the degree of the numerator is less than the degree of the denominator, of course, because the degree of the numerator is just 1, and the degree of the denominator is 2. Let's see if we try x squared over x cubed. Same thing. We could even try putting in some other terms like x squared plus 3x plus 1 over x to the third plus 6x plus 2 or something. And yeah, as you can see, it still forms an asymptote on the axis. Okay, what else do they say? They say that if the degree of the numerator equals the degree of the denominator, then you're going to have a different horizontal asymptote. You'll still have a horizontal asymptote, but it's going to be located at a special location that's determined by the coefficients of your largest terms of your polynomials. So take an equation like f of x equals 6x squared over 2x squared. What they're saying is that these guys are going to have a horizontal asymptote, but it's not going to be on the x-axis. It's going to be at a location that's based on the coefficients of your polynomials. So just to, make this clear, this is n, the exponent of our numerator polynomial. This guy is m, which is the exponent of our denominator polynomial. When they say an, they're referring to the coefficient of the numerator polynomial. And when they talk about bn, they're talking about the coefficient of the denominator polynomial. And they're saying when n equals m, then we're going to have to divide an by bn, to get the equation of the horizontal asymptote. Apparently, it's at y equals 3. So let's try that on Desmos. Okay, yeah, here's 3. Y equals 3 is the horizontal line. Yep. And that is the asymptote. This is an interesting one because it doesn't have any shape other than a horizontal line. But we could add a whole bunch of other terms to the thing, and as we can see, it really doesn't matter what those other terms are when it comes to finding the asymptote. You still got an asymptote at 3, no matter what terms I add onto this thing. That's kind of neat. Okay, and then let's see. The other types we might get would be, what if our numerator degree is 1 more than the denominator degree. So that's going to be a case where we can get what's called an oblique asymptote. So imagine taking this 6x squared over 2x squared and now just change that numerator degree to be in 1 more than the denominator degree. So n equals m plus 1 in this case that I just drew. Now what they're saying is the asymptote won't be a horizontal line anymore necessarily. It's going to be an oblique asymptote where you can find it. G is going to be the quotient polynomial obtained by dividing P by Q, where the remainder of the division is irrelevant. So let's try that on the side here. What do they mean by that? They mean you're going to divide P by Q. So P goes in here, Q goes out there. So when they talk about P and Q, they're talking about this whole numerator is the polynomial P, whereas the denominator is the polynomial Q. So if we want to find the oblique asymptote equation, we should be able to find it by dividing the numerator polynomial by the denominator polynomial. Okay, so 6x cubed and 2x squared. Let's see, it's going to go in 3x times minus 6x cubed. My remainder, of course, is 0 here. But like they said, the remainder is irrelevant, actually. So it doesn't matter to finding the equation of the oblique asymptote. The equation of the oblique asymptote is going to be your quotient. And that's going to make the oblique asymptote y equals 3x. Let's see if that is the case. Okay, so we do have a slanted line. Let's see if it matches with y equals 3x. It does. Pretty cool. There's one more possibility. Perhaps the degree of the numerator is more than 1 larger than the degree of the denominator. That would be something like 6x to the 4th over 2x squared. So in that case, n is like m plus 2 in this case. So when this happens, it says there's going to be no straight line, horizontal, or oblique asymptote for the function. Let's see if that's true with Desmos. And of course, we're not proving that it's true because we're not checking it for all polynomials right now. But I'm just doing one example to see if it goes along with what they say the rule is, right? Okay, so yeah, if we do 6x to the 4th over 2x squared, we do not get a function that has a straight line asymptote at all. So I guess it looks like the rule holds there. It says here the function x squared plus 3x plus 2 over x plus 1 has no vertical asymptotes. We looked at this one earlier. It was right here. We showed that its denominator completely canceled, and that's why it had no vertical asymptotes. But it doesn't mean that it doesn't have any asymptotes. For this function, when we do the reduction, he reduces to x plus 2. That's what we revealed earlier. That's because x squared plus 3x plus 2 breaks down into x plus 2, x plus 1. And then the x plus 1's cancel. So he can be rewritten as x plus 2. Now for this function though, let's look at the original. Our n is going to be the degree of the numerator. And our m is going to be the degree of the denominator, which is assumed to be a 1. So let's write those down. For this function, n is 2 and m is 1. Since n is m plus 1, we have a line that we can make that's going to be the oblique asymptote. So it's going to be g of x equals the division of p of x over q of x, but we don't include the remainder. Okay, so let's divide these two on the side. Alright, so x times x makes x squared. 3x minus x makes 2x. X times 2 makes 2x. And we get a remainder of 0. And our quotient here is going to be the oblique asymptote. Okay. So it's x plus 2. Alright, here's another example. X squared plus 1 over x plus 1 is the rational function. As we can see, the n is 1 bigger than the m. Okay, so here n is 2, m is 1. We see that n is m plus 1. Therefore, there's going to be an oblique asymptote. So let's now divide x squared plus 1 over x plus 1. Let's see, now we'll subtract. X times x makes x squared. I have to move this plus 1 over. Let's see. Minus x makes negative x. Bring down the plus 1. And we'll multiply by like a negative 1 there. And let's see, we're gonna subtract now. Negative x minus 1, looks like. So here we get a remainder of 2. But that doesn't matter when it comes to the oblique asymptote. The oblique asymptote's just going to be g of x equals x minus 1, which was the quotient of the division. We just basically don't even worry about the remainder. For this function, n was 2, m was 1, quotient was x minus 1. They also, I think, want the 2 over x plus 1 there, but we don't worry about this part, so we just make it x minus 1.